For those of you who are new to the series, welcome. I'm Sam Foster, an application scientist here with Axcend. We make compact capillary scale liquid chromatography systems. And so as part of kind of getting our name out there, we wanted to do this webinar series on various differences between your standard HPLC and capillary scale HPLC. And so if this is a series that you find interesting, we hope you'll check out the rest of the series. It should be up on our website, which we'll be linking to a little bit later. For today, we're going to be talking about ways to reduce extra column effects and really talking about why that is so important when working on the capillary scale. So as an outline of what we're going to be going over today, I always like to start by discussing what chromatographic scale is and what I'm talking about when I say we operate on the capillary scale. From there, we'll go into what extra column band broadening is, why it matters more in capillary, and then we'll go through all of the different areas that tend to produce this extra column band broadening and ways that you can mitigate them. So first and foremost, for our repeat viewers, I'm sure they've seen this slide a bunch. Chromatographic scale is typically defined based on the inner diameter and therefore the flow rate of your column. So as you shrink the inner diameter, the flow rates needed to achieve the same linear velocity or speed that you move through the system goes down dramatically. So if we take a standard 4.6 millimeter ID column, these, are your sort of go-to for a lot of older analytical methods. Typically, you'll run those about a milliliter a minute. If you wanted to achieve the same linear velocity on, say, a 2.1 millimeter ID column, you would have to operate at a flow rate of 0.2 milliliters a minute. But when we go down to the capillary scale, we're typically using columns that are about 0.3 millimeters in inner diameter or smaller. And so in this case, about 4 microliters a minute would give you the same flow rate. So when we go down into these capillary scales, the flow rates get shrunk dramatically while the chromatography stays the same. Now, in terms of extra column band broadening, I think we need to start by defining what band broadening is as a whole. So as soon as you inject your analyte into the system, you effectively inject a band. You can think of it as a little rectangle of your analyte that moves through the system. And as it moves through the system, it's going to slowly spread out or broaden due to a number of different factors with diffusion and flow profiles, and as we'll get into a number of different areas. But what makes extra column band broadening different is that band broadening is typically defined by 3 different aspects, and you can see it there on the top, your total band broadening. You'll see this unit sigma squared. This is a measure of variance, and so it's effectively how wide your band is. So you'll see a lot of that sigma squared coming in today. And the total band broadening of the system can be summed up as the band broadening of your pre-column, the band broadening of your column, and then the band broadening of your post-column. And while we've talked about a lot of the column differences in HPLC in our previous webinar, what we're going to be focusing on today is the band broadening exclusively due to the extra column effects. So the band broadening of your pre and post column volumes. And so taking a brief look at some of those different points of band broadening, we'll see band broadening from the moment of injection, so band broadening from your injector. You'll see band broadening due to connected tubing, and we'll go through a little bit of that, but also band broadening from your connections and unions. If you don't do those properly, you could run into issues of increased band broadening. The same on the post column, right? We again have tubing and connections, but we also have band broadening that occurs in the detector because band broadening doesn't stop until you've finished and it's gone out. In fact, it doesn't stop then, we just don't detect it. So basically, every aspect of the system has to be looked at in terms of its ability to influence band broadening. Now, why does that matter so much on the capillary scale? A lot of it comes down to the flow rate and just the sheer differences in volume between the analytical scale and the capillary scale. A microliter of void volume on the analytical scale doesn't matter that much. You're running at a milliliter a minute, you'll clear through that volume very quickly. On the capillary scale, a microliter of dead volume would result in a minute of total extra broadening. And so as you reduce these flow rates, the impacts of your extra column volumes and your extra column effects become very, very felt in terms of your chromatographic performance. So for this, I wanted to give just a brief explanation of the differences in flow rate. So if we model it using a variation of the Taylor-Arras diffusion, which you can see the equation for that on the top, if we were to take a standard piece of this red peak tubing that you're used to, so say 25 centimeters long, and red peak has an inner diameter of about 127 micron. If we had a peak that was 30 seconds wide on the analytical scale, that tubing run at a milliliter a minute would add about 0.006 seconds to the width of that peak. So a very, very negligible amount, because when you're going through that tubing, you're going through quickly and it doesn't necessarily have time to experience the diffusion and the broadening. If you took that same piece of tubing, but put it onto the capillary scale, we would see about a 6.18 second increase. And so that's about a 20% broader peak due to a single length of 20 centimeter peak. And so minimizing these volumes and the impacts of tubing is one of the key considerations when you're working down at these lower flow rates. So in terms of best practices when you're working on the capillary scale, you want to ensure that you're using the narrowest inner diameter tubing possible within reason. Because again, as you start to shrink these inner diameters, now you're using very, very small ID tubing that has the potential to clog. It also has the potential to dramatically increase the back pressure of your system. And so to show that, if we were to take that same 20 centimeter length of red peak from before and run it at a microliter a minute, we see its expected variance, or its expected sigma squared, of about 25.5 seconds squared, and it would cause about 0.05 PSI. If we were to then shrink it to a 20 centimeter length of beige peak sill, which is about a 50 micron ID, we would see that sigma squared drop dramatically to about 0.61, and we would see an estimated back pressure of about 2.4. And so if we go even further and have the inner diameter of that, and we use orange peak sill or 25 micron ID, we're now at a sigma squared of 0.03 seconds squared. So much, much less variance than what we would see with the 127 micron. But we also now have 38.8 PSI at a microliter a minute. And so this can get out of hand very, very quickly. If we were to, again, shrink it to, say, 10 micron, you'd be looking at several hundred to, potentially thousands of PSI, depending on your flow rate and your length of tubing. And so there's a balancing act that has to be made when you're working with these tubings. In the case of best practices, you typically want to use either 25 or 50 micron ID tubing. At lower flow rates, you tend to opt toward the 25, and at higher flow rates, about 10 microliters, you want the 50 micron tubing. Again, also be sure to factor in things like clogging. If you're working with very salty solutions or solutions with a lot of particulate, you may want to go with wider tubing. Now, this is another area that can be of considerable band broadening, and that is uneven cuts. So a lot of capillary scale came from the use of coated fused silica capillaries. And so with those, typically you would cut them with some sort of ceramic edge, and that produces a very easy cut. And so tubing can be modified to the desired length. However, as we can see in this figure over here, if you don't get that cut perfectly flat, you can introduce void volumes. And what those do is they'll dramatically increase your band broadening. I mean, we saw the dramatic shift from an 100 micron ID tubing to a 25 micron ID tubing. That maybe cut out portions of a microliter. In here, this can introduce that same, potentially microliters of dwell volume, which can result in significant peak tailing. It can result in poor retention times, poor repeatability, and really, really damage your chromatography. And so if you're purchasing tubing, manufacturers will often pre-cut it to the length that you want, and those will be pretty flat and polished connections, provided you take care of them and don't chip them or rub them on something with, a high grit. If you do have to custom cut your own lengths of tubing, there are polishing kits that can be used to smooth down that face and get it to a nice, perfect flat fit, because tiny little differences, if it has an angle of 1 degree away from being flat, that can result in considerable peak tailing. And so it's very important when you're making these connections to ensure that you're doing absolutely everything necessary to cut out that dwell volume. Another aspect that a lot of people don't think of normally is the idea of changing inner diameters. So when you're flowing through a tube of a fixed inner diameter and you either shrink or increase that inner diameter, you'll get these sort of zones of pore mixing, or zones of you know, currents that will disrupt the laminar flow. And so in basically every case, your ideal is to ensure that you keep the same inner diameter wherever possible. That'll come up in a little bit when we start talking about unions and bore sizes. But when you're connecting even just 2 tubes together, you want to ensure that you keep as little variation in the inner diameter as possible, as those little poorly mixed regions on the edges can result in peak tailing and can also result in the potential for split peaks. And so it can damage your chromatography there as well. One final one, and this is, a little bit more analyte specific than sort of the previous ones. A lot of larger biomolecules, although small molecules can also experience this as well, can have non-specific interactions with different types of tubing. For a lot of the larger biomolecules, you tend to see this come up with when working with metallic tubing, like stainless steel. You can get a lot of adsorption, so you'll see reduced peak heights. But you can also get a lot of tailing, as these have interactions that aren't necessarily the interactions of your column. And because you have a lot of that metal in your tubing system, they can have outsized impacts toward your chromatography. And so the figure there we see on the right is the difference between a stainless steel column and tubing, which you can see is low and extremely broad, then shifting it to a surface modified system with a surface modified column. And again, you can see a very significant decrease in your overall intensity, but a little bit better tailing. And then if you have a fully compatible system and a fully compatible column, you see very, very low tailing and a dramatic increase in your overall signal. And so a lot of this is analyte specific. You want to ensure that whenever you're doing a separation, you're using tubing and solvent facing materials that are compatible with your analyte that won't produce these types of interactions. This one, they have various options in terms of biocompatibility, different peak tubings to cut out the potential for metal interactions. Again, this is not an easy one to say, because it does change per analyte, but you always want to ensure that every aspect of your system is not interacting with your sample as much as can be done. So we've talked a lot about the tubing. Now I want to move forward into a lot of the connections. So when making fluidic connections, sort of the most common way to do things is to use a ferrule and put your tube in and pinch that ferrule or that frit down onto the end of your tube. And this works really well. You can get very high pressures. It's done pretty simple. You screw it in and put it a little bit of a turn further, and not much happens. What can come from this, though, is that many column manufacturers have different lengths in terms of their overall space inside of the column. And so what you can see there on the right is if you have too long of a stem or too long of your tubing, as you shift from one column to another or shift from one depth to another depth, you can see the stem gets too long, your ferrule can't properly seal it in, and you'll have leaks or void volumes that'll result in poor chromatography or no chromatography at all, because you can't get fluid through the system. On the other hand, if it's too short, you get a lot of dead volume, right? You can again have one of those voids, which will result in mixing, increased peak tailing, and overall much worse performance. And so when you're working with these systems, it's best practice if you're using, fittings that will, and we'll get into a new type of fitting soon, But if you're using fittings that have a pinched ferrule depth that you can't necessarily change afterwards, it's best practice to make sure that one, you properly set that, but two, that you make sure that if you're going to switch it to a different connection, you reseat it or use a different tube to ensure you don't produce those leaks or void volumes. Another key thing is don't over tighten. A lot of capillary scale is done with 360 OD fittings. These can be very, very small, and the tubing itself can also be very small, and so it's very easy to turn too tight and crush them. Best practice is if you're working with something like metal, you want to do finger tight plus a quarter turn. If you're working with something like PEEK, you want to just do finger tight, as it's very easy to damage these small capillaries. Now, if you don't necessarily want to work with, reseating and redoing your fitting every time, you can use this newer technology of face sealing fittings, which has seen a lot of interest in recent years. And so what this features is a very long stem, which on the end of it has, it's typically PEEK, a small amount of deformable material that will press into whatever depth is possible and fill the volume out. So you don't necessarily have to worry about the leaking from a too long of a stem, and you don't have to worry about too short of a stem because it was intended to go as long as possible. So this allows for very reduced void volumes. It's reusable across multiple different depths, and so it's incredibly useful on the capillary scale because this limits the need to set a new fitting each time. They're often finger tight, so you don't have to worry about crushing the capillary. And because the face sealing does deform to fill that space, if there are minor nicks and, it maybe isn't necessarily the most flush if you've custom cut your length of tubing, it can pull a little bit of its weight and try and fill in some of those voids. Now, obviously, you want to ensure that it's as flat as possible, but this gives you a little bit of additional wiggle room compared to just your traditional fitting. And so these are going to be very heavily used throughout the Axcend system, as we'll talk about a little bit later. But it's great practice to use these when trying to reduce your void volumes as much as possible. Now, on top of that, when we're making these connections to a union, you want to make sure that your union has a bore size that is compatible with your system. So the bore is that narrow bit of tube that you can see highlighted in the figure there. That bore size does also act like a length of tubing. So if you have a very wide bore size, you'll see a very considerable amount of broadening. So the goal is to keep that bore size as small as possible. That being said, as we talked about with the mismatch of inner diameters, you want to try and keep that bore size to be as matched to your system as possible. So if you're using 25 micron ID tubing, you want to use a 25 micron ID bore. If you're using 50 micron ID tubing and you have 25 micron ID tubing on either side of it, you may see some increased PEEK broadening because of that mismatch of inner diameters. And so even though it's possible to go to reduced inner diameters compared to or reduced bore size compared to your tubing inner diameter, it may not always be the best for your chromatography. So it's something to consider when you're working with these unions, that you want to ensure that it has as stable or straight a path as possible. Now, this is only for unions that have an internal bore. If we look at some of these other unions, there are zero dead volume or zero volume unions. So in zero volume unions, you have two lengths of tubing with identical inner diameters, and you press them perfectly flush against each other, resulting in no void volume between the two. These can be a little bit difficult to set up. It's a little tricky, but they're incredibly useful in terms of limiting your overall volume. Then we have zero dead volume unions. In this case, you want to ensure that the amount of volume the union has is as low as possible, and you match the IDs to the bore of the union so that it's almost as if the union was never there. The analytes flow through in a straight shot, and you don't necessarily have to worry about any amount of increased band broadening from the union specifically, as it acts like just another length of your tubing. So finishing up on the tubing and the fluidic connections, we also have to consider that the injector acts very much like a union. right? There is a length of bore size, or there is a bore size within the injector. There is lengths of tubing within the underside of the stator to have your actual injection loop. And in fact, the amount of injection volume that you put in, and we've discussed ways to scale injection volume a little bit before, but the amount of injection volume also plays a role on your chromatography. And so there's some best practices you can do to ensure, the least amount of impact from your injector. First and foremost, you want to make sure that you have minimal bore and groove sizes. You want to keep those as low as possible. And if possible, you want to match them to the ID of your tubing. You also want to ensure that your injection volume is sufficiently low. Best practice is typically less than 10% of your column volume. This can often result in nanoliter sized injections when you're working on the capillary scale. There is also the potential when you're doing these injections, as we'll go over, to overload the column. In those cases, you'll see decreased peak shape or potentially breakthrough. And so we'll cover it there. But there are some further best practices you can do when trying to optimize your injection. Looking over at the detectors, so this is sort of the last part of your system. When you're working with detectors, it has to be a balancing act between having sufficient sensitivity and limiting any type of broadening, especially with optical detectors, which is commonly used for absorbance detection. These detectors typically have a path length, right? And if you think about Beer's law, where absorbance equals EBC, your path length plays a considerable role in the actual signal that you see. The longer your path length, typically the higher absorbance you'll see. Now, that isn't always the case because that path length does count as tubing. And the longer you're tubing, the more broadening you have. And so you have to factor in that even inside of your detector, you're going to be experiencing broadening. And we'll get into this a lot more when we start to discuss the capillary detectors, which should be our next installment of this. Flow cell design plays a role, flow cell length. There's a whole bunch to it, and we'll be talking about that for an hour next time. So I'm going to brush over it today. There is another solution. There are often on capillary detectors or non-contact detectors for some of the electrochemical detectors. These are ways that you can properly detect the system without introducing additional dead volume. So for on capillary detectors, you would actually slide the detector across the outside of the column so that at the exact outlet of the column, you're able to detect and shine that light straight through the capillary and collect it on the other end. Now, the limitation with these is that you are limited to the path length of that tubing, and you want to ensure that that tubing's inner diameter is as low as possible. And so typically you are running with path lengths of 50 micron or 100 micron, which dramatically lowers your overall sensitivity. And so when working with detectors, it's important to balance the volume of the detector with its overall impacts on broadening. And we'll be going over that in more depth next time. Another aspect I wanted to add is that it is possible that your detector is also causing broadening due to improper settings. So in the case of this, if you're working with very narrow peaks that are seconds across, typical detector response times and acquisition rates can be mismatched to what you're seeing. There's a lot of best practices in terms of how many peaks or how many points you should have across a peak. It varies. I've seen 40, I've seen higher, I've seen lower. But it's important, and we'll get into exactly how to optimize that. But it's important to ensure that when you're doing these separations, if you have a peak that has a width of 1 second across, that your board has a response time or your detector has a response time to accommodate that. If your detector has a response time of 1 second, meaning it takes 1 second to shift from no signal to, I believe it's 90% of the signal, that would mean that that entire 1 second peak is now broadened out very considerably because the detector itself is trying to filter that data and ruining your chromatography. And so we'll go into that a little bit more in the next installment, but I wanted to bring that one up. So some good advice if you're looking at your chromatography and you're starting to see some issues. If you see long tailing peaks, this isn't always indicative of void volumes in your system. It could be mismatches with analytes or a whole bunch of different issues chemically. That being said, it also could be indicative of various different issues that we've discussed today in your system. So it could be a mismatch in tubing inner diameter that's causing those small little poorly mixed zones. It could be that you don't have a perfectly flush face on one of your tubes, causing that void in there. Basically, if you're seeing peak tailing and you're not so sure how to fix it, great practice is to go through and check that all of your fluidic connections are made properly. If that's still tailing, then you can start looking at a lot of your chemical interactions. In terms of peak fronting, so this is one of those areas where if you use too high of an injection volume, you can overload the column and see a very long creep up to the front of your peak. In these cases, you want to see if you can reduce your injection volumes to be much lower than that. That often will fix it. Another issue could be that if you are doing some of these larger volume injections, if they're made up in a stronger solvent than what you're running, so for example, if you're doing a 5 to 95% organic gradient, like you would see in reverse phase, but your sample is made up of 100% organic, and you put in too high of a column volume, you can see poor or even no retention because that high organic slug or that high organic band hasn't broadened enough and will simply go straight through the column with your analyte unretained. So best practice is to try and match your sample solvent as closely as you can to your mobile phase conditions to ensure that you don't experience peak breakthrough. So moving forward, I want to talk a little about how Axcend has optimized and used a lot of these learnings on our system. First and foremost, we have adjustable injection volumes ranging from 4 nanoliters all the way up to 1 microliter. 1 microliter is ridiculously large and way blows past that 10% of column volume rule. That being said, it is still possible, and so we do offer it, but it does come at the caveat that you should probably consider doing something smaller first. We do have small inner diameter and short length tubing. We are a very compact system, and so basically all of our connective tubing is centimeters in length and typically either 50 or 25 micron in inner diameter. So really trying to reduce the broadening effects from tubing. We also use passivated stainless steel. So for those non-specific interactions, particularly in biomolecules, you'll tend to see reduced or even no impact from the system there because of the passivation. On top of that, we offer a number of different cartridges. So this is our fixed column cartridge. In this case, we've custom packed a capillary column to go into the cartridge. And then we have that on capillary detector that I've mentioned there. This connects into the system through face sealing fittings, so it makes void-free connections. And that allows for high efficiency chromatography without any additional post-column broadening because the on-capillary detector doesn't introduce any extra volume into the system. On the other hand, because the fixed column cartridge doesn't necessarily have the same path length, it is often less sensitive, as we'll talk about in a little bit. And so when higher sensitivity is needed, we offer a heated column cartridge. In this case, again, we're using those same face sealing fittings and short connective capillary tubing to connect to the system and to the column. We're using a narrow bore union, which is matched to our tubing IDs. Pardon me. But here we introduce a low volume flow cell. And so rather than having your path length be determined by the inner diameter of your tubing or the inner diameter of that capillary post column, instead we have a fixed path length of 1.2 millimeters, I want to say. And that will dramatically increase your sensitivity while also keeping your overall volume low. So what does that look like? Well, we compared the same separation. This is a separation of alkylphenones between your on-capillary detection and your flow cell detection. And so we see about an 8-fold increase in path length, which results in about a 7.8 times increase in your overall sensitivity. So we're seeing dramatically higher peaks over on the flow cell, but we aren't seeing them exactly as high as we would expect. And so that missing 0.2-fold increase is coming from that introduced band broadening. Now we could see here we're still achieving very high separation efficiency, and we're able to do so due to a lot of the mitigations and the limitations of extra column volume. So in conclusion, extra column band broadening has increased impacts when you're operating down on the capillary scale. Those lower flow rates tend to exacerbate the issues. When you're using shorter, narrow inner diameter tubing, you can improve your performance, but you also have to keep in mind that the smaller inner diameter you go, the higher chance you have of clogging, or even just the higher pressure you have in standard operations. When you're making these fluidic connections, you often want to use space sealing fittings. They offer high pressure connections while really reducing or in fact eliminating potential void volumes. It's best practice to tailor both your injection and detection systems to limit the amount of broadening that you need. And finally, Axcend has kind of taken all of this together and put it into one system that's highly optimized to reduce a lot of that extra column band broadening. If you're interested in getting to know more about capillary chromatography or interested in being a part of the community, whether you're an expert in the field or completely new, we urge you to stop by and visit our LinkedIn group. You can join with the QR code on the screen. Anyone is welcome. There we have people ranging from experts to complete beginners, so you can ask questions and really get to learn from the group and build a community. Here are the references that are listed in each slide. And with that, I'd like to thank everyone for attending. If you liked what you saw here today, this is, I think, part 4 or 5 in our ongoing series. And so the others are up on the website. Feel free to check it out. With that, I will go ahead and open the floor for questions. All right, first question. In the heated column cartridge, what is the inner diameter of the connective tubing pre and post narrow bore union? And what is the inner diameter of the union? Are they the same? If not, is this something Axcend is looking to improve? So they are slightly different. It is a 25 micron ID tubing with a 50 micron ID bore size. And so there is a slight difference there that will cause some band broadening. That being said, the actual volume of the union and the amount of broadening caused by that is fairly low. We are looking to improve that. They don't make 25 micron ID or 25 micron bore size unions. We are looking to eliminate that union completely, as any union there will cause extra column band broadening. And so it is something that is an ongoing development project, and there are a lot of really cool ideas we have to limit that. So stay tuned, because it is something where we can get even better. I see another one here. I mentioned that small ID tubing can increase pressure. How do you find the right balance between minimizing dispersion and avoiding frequent clogs? So first and foremost, one of the best tips that I can give for avoiding clogs is filter solvents, filter samples. Anything that should be going through the system should be filtered. We recommend a 0.22 micron filter. That tends to get you very, very good filtering to avoid all of that. That being said, it is a balancing act. So the higher you go in flow rate, typically the larger ID tubing you can tolerate. We have a paper that I believe specified the cutoff limit as below 5 microliters a minute. You want to be at about 25 micron ID tubing. And above 5 microliters a minute, you want to be at 50 micron ID tubing. That being said, that's kind of more general practice. In our case, we keep 25 micron ID tubing post-column, but 50 micron ID tubing pre-column, because any potential particulate would be stopped by the column there. And so you can get away with having narrower tubing post-column because it acts like a large filter. I see another question here. Are there practical differences I've seen between face sealing fittings and traditional ferrule-based fittings when switching columns frequently? It's a rare but not impossible occurrence that these face sealing fittings, because you are deforming a material over and over again, you can run into instances where it gets visibly deformed or visibly a little bit messed up on the end of the face sealing fitting. When you're swapping columns, every day, 5, 10 columns a day, it can run into some difficulties there. That being said, typically that occurs after hundreds or thousands of swaps. And so it's not something that you would need to really keep in mind for general use. Maybe over, a year or two, you'd probably want to swap out those face sealing fittings, but it's a fairly inexpensive part, and they're becoming more and more common. Right. Any other questions? Here's one. When troubleshooting peak broadening, how do you tell if your problem is coming from tubings, fittings, or the detector cell? I think that's a great question. So first and foremost, I like to work backwards. So I would look at the last part of your system first and work from there. So I would take a look at your detector cell. How much volume does it have? Is it leaking in the connections leading up to it? Is it optimized for capillary scale? If it is, you can feel free to move past that. We'll again talk about response factors and things like that. So then I'd move backwards to fittings, right? Are your fittings working properly? Are you using the right limitations with tubing? Is your tubing cut flush? And so really starting at the detector and working back and back and back and eliminating different pieces as you go will allow you to more easily narrow something down. Right. I see another question here. Can I talk more about how mismatched tubing inner diameters influence flow? Does this impact peak shape or retention time consistency? It can have small impacts on retention time consistency depending on how large that shift is. Really, what you'll see is one, a broader peak or potentially a very highly tailing peak resulting from that. And a lot of it has to do with just how consistent, or sorry, how considerable the shift in inner diameter is. So if you're going from a 25 micron to a 50 micron, it's fairly limited. If you're going from a 25 micron to, a 200 micron inner diameter shift, those voids will become much more consistent and have a much larger impact on your overall system. All right, I see another question here. How much of a difference does using biocompatible versus standard stainless steel tubing actually make, or how much of a difference does it make in routine small molecule? So really where you're going to see the impacts of these is in large molecules, more often than you'll see it in small molecules. In large molecule work, it can make a very considerable difference. It can often take 10 to 20 injections before you even see analyte because you're simply losing it to the metallic tubing as it gets absorbed. That being said, it is not unheard of that small molecule work can be impacted by stainless steel tubing, depending on your analyte, if it has something to do with chelation, depending on your stationary phase, right? Metallic ions can often mess with some of the different separation phases like ion exchange. And so it's important to make sure that, regardless of your work, you're picking tubing and a system that has solvent facing materials that are compatible with what you're trying to analyze. All right. I think that is all of the questions. So I'd like to once again thank everyone for coming. If you have any further questions, please feel free to reach out to us or visit us on our website. And with that, thank you all for coming. And I look forward to seeing you all next time.